Hi students, welcome back. In this video we're going to do a brief extension to our mole conversions. In the previous video we did the bulk of the mole conversion lesson, and in that video I taught you that stoichiometry is just the use of the ratio, and that's really it. It's using your coefficients and making a ratio out of it. And what you may or may not be getting held up on right now is the prepping and the polishing work. And in the last video where we started this for you, all we've worried about is grams. So we did gram to mole conversions in the prep step, and then if we had to polish it off, we went from moles to grams. And our conversion factor was the molar mass of the substances we were looking at. So molar mass will always change a little bit in these conversions. And we did one step, which was just the ratio, two step, in which we had to either prep or polish, but not both in any one problem. And then the last section, which you probably started on in this week's lesson, was going mass to mass. So all the way, three-step problems where you had to prep, use the stoich ratio, and then polish it off. And again, those prepping and polishing change because the molar mass for every substance is different. In today's extension, we're going to think about a new way to prep and polish when we have gases, and specifically when we have gases at standard temperature and pressure. We have a conversion factor that allows us to convert from liters of a gas into moles of a gas. And that new conversion factor will be the same for every gas, and it's 22.4 liters of gas per mole. And that's at STP. And that will not change. It will be the same for every gas. So that's the good news. Now, I'll give you a couple of example problems here that we can use and apply this new conversion factor to. In this first problem, we're combusting propane, and we're combusting it. We have 18 moles of it, and we're using excess oxygen. So some of you are still unsure about what that means. If we have excess oxygen, that just means I have more than I need, way more than I need, so I don't really have to worry about the amount. Just kind of ignore oxygen. How many liters of CO2? All right, so here CO2 is a gas, so this will work on CO2. Can I produce? And very important, we have to either assume we're at STP, or better yet, we know we're at STP. All right, so going back to our original information given, we have 18 moles of C3H8. Tell you what, before we keep going, let me lock this focus. There we go. All right, so we have 18 moles of C3H8, and we are going to, since we're already in moles, there's no need to prep. We're ready to go right into the stoichiometry step. So moles of propane, and we're converting into moles of CO2. So this is just our ratio, and it's a 3-to-1 ratio from the balanced equation. All right, so that's the old stuff. Now here's the new stuff. We'll just add one more step here. We've crossed out those moles. Now we want to cross out the moles of CO2. And we want to go to liters of CO2. Well, here's where we use that new conversion factor that I showed you. 1 mole of any gas at STP occupies 22.4 liters. It's just a fact. So that gets rid of your moles, and we'll get the calculator out, and we will have prepped, and well, we have to prep. We will have ratioed and then polished this one off. So 18 times 3 times 22.4. All the numbers are on top. So that means we get, let's round this to 3 sig figs, 1,210 liters of CO2. Simple as that. All right, so you may be wondering how in the world this 22.4 comes about. Some of you don't care, and that's fine, so you can take it as fact if you want. But for those of you who are wondering where it comes from the ideal gas law. One of the reasons we did the gas laws first. So very specifically here, we're looking at liters, so that's volume. So we've learned that we can rewrite this as nRT over P. And if we simply plug in, what if we only had 1 mole of any gas? And let's choose the 0.0821 R value that has the atmospheres in it. And now standard temperature, that's important, remember we are at STP. Standard temperature is 0 Celsius, which is 273 Kelvin. And standard pressure is atmospheric, which is very easy if we use 1 atmosphere. That's why I chose that R value. So once again, if we take our calculator and run those numbers, 1 times 0.0821 times the 273, and then of course divide it by 1, which isn't going to change anything. Here, I'll do it just to make some of you happy. Look at the number I get, 22.4. And if we round that to 3 sig figs, folks, that's where our conversion factor comes from, 22.4. But again, that was for 1 mole. And if you look at my unit up here, it's per 1 mole. And so really all we're doing is doing sort of a Pivnert ratio in our head. Well, we would really be running this calculation with 3 moles. Like we take our answer right here, plug it in, and then just run it again. But since gases are so consistent, we can just use this 22.4 and multiply it by our answer, and we'll be good to go. Saves a little time. All right, so let's finish this second example here. So this is N2O5 gas, dinitrogen pentoxide. I'm going to react it with some water. And this time, I'm starting with 225 grams of water. Well, water here is a liquid, so my 22.4 won't work. And this is in grams, so I can't use my ratio yet. So I do have to prep this problem. Got to do a little prep. So we're going to convert grams of water into moles of water. Now using our molar mass, 2 H's and 1 O, the molar mass is 18. If you need to hit pause that and calculate it to yourself and verify that it's correct. And so that puts me in moles of water. And at this point, we're just going to do a conversion. Moles of water, this is our stoichiometry step. And we're worried about N2O5, which is the other reactant, and that's perfectly fine. So we're just really converting moles of water into moles of N2O5. It's kind of a lame problem, but it's just a 1-to-1 ratio, so nothing's going to change. We have the same number. The problem wants liters of that N2O5, so I need to polish this one off to get it out of moles. So I'm going to put moles of N2O5 down here, and I'm going to convert it to liters. And as we've just discussed, 1 mole of N2O5, any gas, has a volume of 22.4 at STP. So let's get our calculator back out. I'm going to run this one, and I'll write the answer down below it. All right, so 225 divided by 18. The stoichiometry step is useless, it's just 1. So let's go right to 22.4. And that tells me 280 liters. Sig figs aren't exactly right on that one, but it worked out right on the money, so why mess with a good thing? Alright, so that's using molar volume as a prep and polish step. I didn't do an example of using it as a prep step, but it would work the same. Just make sure you use your dimensional analysis. You know that if you multiply it in a polishing off step, if you had to do it at the beginning in a prep step, it would be divided by. Same action as the molar mass. If you have any questions on this or how to use the molar volume, make sure you ask your teacher or shoot me an email and we'll get it cleared up. That's all for now.